So I'm going to talk about approximation algorithms for Coflow scheduling. I'm Rajmohan Rajaraman. Also, people who have done the real work on this are Erez Kanter and Hamid Jahanjao. Erez is a postdoc at Northeastern. Hamid is a senior graduate student. And actually, Erez and Hamid are also here to answer any questions. OK, so let me introduce the motivation for this. So this is, as we are trying to bucket people and talks into various categories, this is an algorithms talk. And the motivation for this problem is this notion of coflows. So large-scale data processing computations, for example, those that are arising in like MapReduce computations, Spark or parallel programs, Dryad parallel programs, are composed of multiple data flows. And so it's a single computation will be composed of multiple data flows, reducers and mappers communicating with one another. And these flows are running over a shared set of distributed resources. The main semantic aspect that captures coflows is that a single computation that consists of multiple data flows completes when all of its flows complete. Okay? So if a subset of the flows complete, that is immaterial. When the subset of the flows complete is immaterial. So for a single coflow, the computation completes when all of its flows complete. So a coflow is a collection of flows that share the same performance goal. Okay? So that's a coflow. So before I go more into the problem, let me just take a simple example. And this will also sort of state one version of the problem that I will focus on for the most of this talk. So here is a simple 3-node network. And there are 3 coflows in this. There is a blue coflow consisting of 2 flows. And there is a green coflow going up like that, which consists of only 1 flow, and a red coflow consisting of only 1 flow. So the blue coflow has 2 flows, one requiring a demand of 1. So imagine 1 unit of transmission between these 2 nodes, one a demand of 2. So 2 units of data needs to be transported across this link. And the green flow requires 2 units to go across that path, and the red one unit to go across that. So that's the setup. Assume that every edge link here has unit capacity. OK, so now in this situation, let's say our goal is we would like to complete these coflows as fast as possible. And for this purpose of this talk, we're going to be focusing on average completion time of the coflows. So each of these coflows has the same weight, and we want to finish them on average as fast as possible. So what could you do? So what are we allowed to do? Well, we could do the following. We could assign a constant bandwidth of half to every flow. There are 4 flows. We can assign a constant bandwidth of half to every flow. Why half? Well, these blue and red can only get half bandwidth because the bandwidth of this link is, the capacity of this link is 1. Similarly, the blue and green can only get half at any point of time if they're going together, because on this link they can only get half. So we do, let's say, half. So this is what is illustrated here. So the A flow, which is part of the blue, gets half for 4 units because it has to take 2 units of transfer. B takes 2 units, half. So you see everything. So since blue is a coflow, these 2 blue flows form a coflow. Its completion time is 4. The green is 4. The red is 2. Okay? So you get a total completion time of 10. Okay, well, if you think a little bit more, you might say, okay, you can do better, perhaps. How about we give blue more priority over red and more priority over green, say? So you do the 2 blues first. So you start blue on the 2 blues first. But by the time, so the B flow finishes within 1 time unit, so you can start the red, and you can start the green at time 2. So you get completion times of 2, 4, and 2, okay, for a total value of 8. However, of course, if you think a little bit more, you can do even better. if you had done the right priority. The reason is unnecessarily we are making the red one wait by giving blue higher priority, even though we know that this flow would have ended later. So this is exactly the notion. The notion of the Coflow tying these two together makes us decide there is no reason to give priority. Okay, so there are actually multiple flow models once you present this in this abstraction, and we have looked at a bunch of different models, and 3 models on which we already have some results, and one other model that we are currently working on. So I'm going to mostly focus on this model, what we are calling circuits or connection based. So here the focus is bandwidth. We are not talking about latency of sort of how long it takes. I mean, path latency is sort of instantaneous. So we are focused on bandwidth, but you can look at latency, and we have. I'll talk a little bit about packet-based coflows, where you're scheduling and routing individual packets that need to be sent from sources to destinations, and so you have to talk about the store and forward routing there. We can also think of coflows as simply tasks, computation tasks, and groups of tasks are put together in a single job, and you're worried about the completion time of the last task in a job, and so on. Okay, so it makes sense in all of these. But the general notion, when we take all of this, the individual flows in a coflow all share a common objective, and we have mostly focused on completion time. Okay, so in this talk, for the most part, we're going to look at circuit-based coflows. So this is not a new model. I think in this, at least the term was perhaps introduced first by Chowdhury and Stoica in 2012, introducing coflows as an abstraction for cluster applications. They're sort of the first, perhaps, serious look at looking at the algorithmic problems here was done by Zhao et al. In an Infocom paper, and they developed a system called a test bed called Rapier, which uses SDN for getting explicit routing and bandwidth enforcement using Linux traffic control. On the theoretical side, Q, Stein, and Zhang presented a constant factor approximation for coflow studying on a specific situation where they're looking at coflows across a non-blocking switch. So it's a sort of for a special topology. And there is certainly more related work on scheduling and routing in data center networks, which I'm not going to talk about. So our focus is on trying to develop provably these are all NP hard problems. I'll say a little bit about the complexity. We are trying to develop provably good approximation algorithms. So the main highlight is we have, for the different models I described, we have been able to obtain asymptotically optimal approximate algorithms, asymptotically optimal approximation algorithms, modulo standard complexity assumptions. I'll focus my attention today on these circuit-based coflows, for which, if the paths are given to you, we give a 4 approximation, while if the paths are not given, we can give a log n over log n approximation. Okay, so just to remind you what the setup is, you're given in our case, an arbitrary network with edge capacities. You have connection requests. Each request has some demand, a source destination pair, and a certain release time. And the requests, as I said, are grouped into coflows. So you have a collection of flow. A coflow consists of collection of flow requests. Each could have their own release time and demand, and so on. With each coflow, we assign a weight that captures the importance of that coflow. And our goal is to find out paths and bandwidth assignment over time for each request to minimize weighted average completion time. Okay. So the way I've stated this problem, it's not even clear how to capture it. I said bandwidth assignment over time. So literally, I'm saying we can give a continuous function over time, which specifies at each point of time how much bandwidth will you give for each flow. So if you think a little bit about it, you can sort of put some of this into notation that captures what is going on. You have a source, destination, demand, release time. You have a graph, capacity for each edge. For each flow, you need to specify a bandwidth for that flow on an edge E time t. Your B should form a flow for each t from a source to destination. It needs to satisfy the demand. So this is since this is a continuous function, it needs to satisfy the demand taken over the entire time. It should always be a flow, so you should never exceed the capacity. You have some completion time. You want to maximize the completion. Okay, so don't worry too much about the notation here because we're not going to delve deep into the notation. So the first thing to observe is, even though we are talking about continuous time, there are some standard and natural statements you can make. So let's suppose a solution you had where you gave a particular flow a bandwidth like this over time, okay, and some other flow a bandwidth like this. Then after that, it didn't get anything, and then you got something like this. Okay, these are two different flows. And let's say there were I consider two time periods of interest. This might be a flow completed or a flow arrived. This might be another flow arrived or a flow completed. But between these two time periods, no such event took place. Then I claim that there exists an optimal solution in which they could actually have been assigned a constant bandwidth across. Why is that? Well, all you can do is assign each of them the average bandwidth that they are getting during this period. Okay? So you assign the red one its average bandwidth during this period, the green thing its average bandwidth, and you do this for every single flow. Since at every instant we have capacity constraints being satisfied, it must imply that when you take the average out, the capacity constraints are satisfied at every instant. And since nothing has happened with respect to the objective function, because nothing arrived before then and nothing departed for then, everything is fixed. And the objective that you get is exactly the same. So this implies that there is a piecewise constant bandwidth. So now you can think about sort of a discrete. I mean, of course, the bandwidth could be any real number, but at least you now have a handle on capturing this without the integrals that I described there. Okay, so that's the first observation. The second question you might ask is, like in that example, we saw that there was a priority order in which we could do coflows. So does it make sense to give a priority order to flows? Okay, so let's take is there an optimum priority order? Okay, it might be difficult to find, but is there one? So let's take another example which will show that, at least in a strict sense, that may not be true. And in fact, sharing of bandwidth, giving a link entirely to one flow or the other is not always the right thing to do. So here is the same triangle, and this is a sort of a slightly contrived example, but can be easily made sort of more realistic. So there are four flows. Okay, each flow is its own coflow. So the blue goes like this, green like this, red like this, and then there is the black flow that goes around. Okay, of course, there is no reason for a flow to come back to itself, but just imagine there are two different nodes sitting here, which there is a long path going between them. So in this case, if you do the following, let's say you assign a half bandwidth to the red, green, and blue, then within 2 units of time they will complete, assuming all the demands are 1. Then within 2 units of time they will complete, and then you can do the black in the 3rd unit of time. So you will get an average completion time of 2 plus 2 plus 2 plus 3 is 9. But if you decide to give the entire bandwidth for a link to one or the other, then since there are overlaps, you can never have more than one flow at the same time. And if you can never have more than one flow at the same time, the only completion time you can get is 1 plus 2 plus 3 plus 4 equals 10. So there is no particular priority order that's going to work in this setting. You have to figure out when to share, when not to share your solution. All right, so what we have observed is even though we're talking about continuous time varying bandwidth, we can actually discretize it to some extent. But it's not obvious whether we can have a strict priority order, whether it's worth getting a strict priority order. So what we do, which actually works across a class of Coflow problems, is we develop an interval indexed linear program. Of course, these time expanded linear programs are fairly standard in scheduling, so in that sense this is not surprising, but perhaps the particular way in which we use is different. So the piecewise constant bandwidth allows us to develop a linear program relaxation that actually achieves the 2 approximation. Notice that it's an LP relaxation. It doesn't capture the entire problem completely because of the continuous, because of the particular nature of the problem, but it gives the 2 approximations. So what we do is we divide time into blocks. So you have 0 to 1, 1 to 2, 2 to 4, and so on. And within a particular interval, we assume that we have a constant bandwidth. Okay? Anything that got released between that interval, we sort of push it later. So that's why we are giving up this factor of 2. So we assume things basically arrive at the boundary. And within this, if anything completes, then we effectively assume that it's going to complete at the end. So these are the points at which we are going to have changes in the system. So then within this, we are talking about a fixed bandwidth for each flow, but of course it will vary from flow to flow. So now we have a constant bandwidth bki for flow I in interval k. We have edge capacity constraints, which I have not stated here. We have cross interval constraints because the total demand that needs to be satisfied across the different intervals for a given flow, because the flow might be partially satisfied here, satisfied here, satisfied here, that should exceed the demand. And there is some objective function. Don't worry about the exact statement of the objective function, which captures things. Okay, so this is the actual linear program. Don't worry about it. From this, we can get a constant factor approximation in the following series of steps. So we solve the interval indexed LP. We assign each flow to the interval that follows the first one at which half of the flow completes. Since these intervals are in increasing geometric order, we can argue with a little bit of work that whatever we are doing in the next, whatever we did before can be actually done in the next interval completely without violating the capacity constraints. The LP constraints and the interval structure guarantee that all the capacity constraints are maintained. The constant bandwidth that we assign to each flow is exactly how much bandwidth we need to assign to complete that within the interval. So the high-level takeaway is that what we effectively are doing is we are grouping coflows into priority groups and putting them in these buckets. But once we come to within an interval, we are sharing the bandwidth in such a way that the coflows complete within those intervals. Okay, so within each group, the coflows bandwidth shares are well specified because we want to complete them within a certain period of time, and we can achieve that. But the main, of course, the way we get these priorities is by solving the LP. So we don't know of any good heuristic at this point of extracting priority some other way than the way we are doing it. Okay, when paths are not given, we can use a fairly standard randomized rounding approach. So we still solve the interval indexed LP before, then we assign flows to intervals without deciding the paths first. Once we have done the LP bandwidth assignment and put them in the right intervals, then we apply randomized rounding to select a single flow for each path for each flow. And then we stretch time by this factor to achieve an order log and order log approximation. And this is the best we can do given reductions from the minimum congestion problem. But all of this allows the directed networks and so on. So it's directed links as well. Okay, so I have just a couple of minutes. So I will quickly go over the differences in the packet-based model. So we also consider a packet-based model. So here again, we have networks with edge capacities. Packet requests. So instead of talking about this, how much I want so much of bandwidth, what we say is, okay, so many packets have to be sent from this sender to this destination. These groups of packet transfers constitute a coflow. We have individual release times, source destination pairs, individual demands. Determine a routing schedule. So you have to specify the store and forward routing schedule. So which packet should be sent when and where to minimize weighted average completion time. The key difference is we are focusing on latency here. Of course, within an edge, the link is being shared, so there is bandwidth sharing there. And the other difference is we are talking about packets as indivisible entities. We are not further dividing packets down into smaller pieces. And so you can also do an interval based expansion here. This illustrates one example. I'm not going to go over.
Right. Yeah. So maybe I missed this. So why is the objective function the sum of completion times rather than the max? I mean, usually like Mixpan, you look at the max, the completion time of the max flow or something.
So no. So you could, if you, that's also a reasonable objective to do max. But then you're doing max over all the coflows. Here we are treating each coflow as an important, as an independent computation. And what you're interested in is the average performance we are giving for all these computations. So each computation is an application. But so we are trying to
potentially unfair to some people.
It is going to be. It is going to be. So the max thing about max is that you're giving the max completion time, especially if you're looking at completion. Now, there are other things you could look at, but if you're looking at completion, as long as you're looking at completion times, and since I'm going to talk a little bit in our framework, we also have release times coming up here. So it makes more sense to do the average performance you're giving to each of the coflows, but max could also be a reasonable thing. If you go with max completion time, then there is no difference between coflows and flows because you're putting all the flows together. Now it's the maximum completion time over everything. So you've lost the notion of coflows.
Maybe I'm not a coflow person, but I thought like coflows have like dependencies across flows.
That's all captured within the coflow. Okay, so within the coflow, we are taking the max of the completion times, right? We're taking the max of the completion times of the flows for a given coflow. Then we're taking the average across the coflows.
Can I clarify that comment? So yeah, coflows is a set of related flows that correspond to the data exchange between two stages of a computation. The dependencies arise across stages. Yeah. So you could have a blue coflow on which a purple coflow is dependent. That has to be scheduled in the future. So here, that's not the model.
Okay. Any other questions? Okay. So the one thing that I wanted to emphasize with this is that you have the problem version we're going to mostly look at is sharing bandwidth. So we are going to assign bandwidth to flows, calculate completion time of coflows, and then average over them. And we are trying to minimize the average completion time. Okay, so the ingredients of a packet-based coflow is interval indexed linear program. The results known, sort of beautiful results of Leighton, Maggs, and Rao from a long time ago on the existence of schedules that optimize congestion and dilation, because now we look at congestion and dilation, congestion at the edge level, dilation at the length level. There are approximation algorithms due to Srinivasan and Teo for finding the actual schedule. So here is where the finding of the schedule will tell you which, finding the paths. This is not finding the schedule, I'm sorry. This is for finding the paths actually. So it'll give you the paths, and then there is a proof of existence of schedules for which there are also deterministic methods to calculate that. So now those schedules, there are relatively easy. So this, to answer your question, Rizul, about the packet routing, there are fairly easy ways to sort of heuristics, which are not sort of FIFO or anything like that, but the way to calculate which packet should be given priority at which switch at what point. So those are there, just from the packet routing literature. This gives rise to a constant factor approximation. Okay, so I'll close with a couple of slides on future directions. So the first thing, this is all theory at this point. Other than the hammer of the LP, the rest of the aspect of the algorithms are fairly straightforward and simple. The one question we have discussed a lot is, can we avoid solving the time interval indexed LP, or can we do something else? And we have spent time thinking about special topologies like trees, which might fit or capture aspects of data center networks. We can certainly, in some cases, we can certainly get simpler and better algorithms, invoking some results about what the LP looks like. And in some cases, we can even get optimal algorithms, but so far not for the general case we're looking at. We could try to improve the hidden constants in the approximation ratio to make it all work. one other thing we could try to do is we could try to improve bounds for restricted classes of Coflows. For example, many Coflows might be such that all the flows in the Coflow share a common source or share a common destination. So one question is, can we do better in those settings? There are other questions about other objective functions. One objective function which seems quite natural to look at is response time, where you look at currently we are looking at a collection of flows coflows that imagine arrive in a sort of certain batch over a period of time, and we want to finish average completion time. And the way we would use it in practice is run this sort of in multiple batches. But it might be better to do this sort of maybe even in an online setting, where we keep track of when they arrive, look at when you complete relative to when they arrive, so look at average weighted response time. You could look at cost-based objectives. We have notion of costs in the weights, but perhaps there might be other dollar figures attached to it, like Bruce suggested we should. One direction which we have spent some time on, and we have some interesting results here, is looking at it, the same question in the optical setting. And here we can, in the general problem, we can actually show a pretty high hardness of approximation. But for certain special classes, there are really interesting connections to well-studied problems for which we have partial results. And as I mentioned, what we look at is completely centralized offline. And SDNs, to some extent, allows us to do it. And perhaps Rasul is going to talk about how to make it distributed in a little bit. But we also look at the offline case. So if the online is of interest, then that's also something we can look at. Okay, I'll start it up there.
Yes. So I thought the LP thing seems good. Actually, I'm wondering about the online as a partner about it, because it seems like the flows that arrive later, because you're going to be exponentially bigger space, are going to get like more hurt. Right? So even though you have two approx, the two approx is not uniformly spread. Like the people coming later are going to get hurt more.
Correct. So I think the way to, if you're to implement it, essentially we will do reset. Okay. You would reset time at various thresholds so as to not hurt the things that are coming late. Okay, so you'll need to. So the objective function. So this makes sense mostly when most of the flows are being released at the same time. If you're looking at an online setting where things are being released continually over time, and you want to, then the right measure is response time, where you're looking at the response relative to when they arrived. So what you would tend to do then is consider a sequence within a period of time, then restart it.
Actually, one interesting thing is, like, if you're actually doing this batching, right?
Yeah.
I mean, what's the value of the interval LP? Because I might as well do batching all the time. I might just do like a really small batch all the time rather than do the interval-spaced LP, right? So what is the interval buying you in that case? So the interval buys you when the so it really depends upon it helps you decide what level of batching that you're doing. So if you're in the objective function we are looking at it's the completion time. Okay, so if there is a lot of stuff that's going to come later, okay, which is going to be completed much later, that's going to dominate in the objective. So if everything is coming relatively so let's say most of the data transfer has been released at a certain period of time, then you want to do your doubling of the intervals until the time all of these things complete. Then you would restart for the next batch of things that are coming up. Okay, so you would basically do that. The specific point at which you will restart will depend upon the rate at which things will be arriving. It also depends on the rate at which things are removed from the system, right? Because some bandwidth is
freed because their demands.
The events are not just released but also like completions.
Their demands.
Yeah.
Yes.
This latent max raw, I thought that was a randomized algorithm, and that all this low-Oz local lemma de-randomizing didn't really de-randomize to deterministic, but to just less randomness. So you said that it's actually deterministic?
So there is questions. So,
Hey, Raj, I know the answer to this.
the max is there.
Kuz is right that the actual,
The original one.
well, the original one's just existence proof. The algorithm for finding the schedule, the actual C plus D, is a randomized algorithm. It's not deterministic.
Yeah.
But I mean, it succeeds with high probability.
Yeah.
And it's nearly linear time.
And okay, so the Mozart-Tardosh results and the variance of that did not apply to.
Use the word de-randomization, but their notion of de-randomization is reduce the amount of randomization. They don't bring it to zero. So.
Yes.
What if the flows are really shallow? In particular, what if the flow is just a collection of edges? Does it make it obviously easier?
What does shallow mean? That collection.
You have a collection of paths, and
Oh, you mean not long paths? You mean just short paths?
Yes.
Then it is. I think it is easy, much easier. Yeah. Yeah. So then it's a little bit like the tasks version that we look at, but the tasks version we look at is only interesting if you had a choice between either put in this edge or on that edge. But if there is no choice and they're all going in the specified searches, then I think it's much easier. Right? It is? Yeah. Okay. Okay.